Hi everyone, I'm Ada Gergen from the Max Planck Institute for Informatics. In this talk, I'll introduce our work Vital, more understandable feature visualization through distribution alignment and relevant information flow. Within mechanistic interpretability, there are two complementary questions, where attribution methods asks which input parts cause the behavior, while feature visualization asks what patterns neurons or networks respond to. Vital belongs to the latter, revealing what neurons represent through faithful and human interpretable visualizations. Classic feature visualization starts from noise and optimizes the input image to maximize the target neuron. It inverts the usual training perspective. Normally, we learn weights given data. Here the weights are fixed and we learn the data itself. Formally, we search for an image X star that maximizes the activation H for neuron I. Despite progress, many feature visualization results look abstract and show repetitive textures rather than recognizable structures. Scaling to larger models is unreliable, and some approaches depend on auxiliary priors, such as gun-based regularization, which can bias the visualization away from what the original network encodes. Vital goes beyond raw activation maximization by matching the feature distribution of the optimized image to the real images, producing non-repetitive, interpretable patterns that reflect intrinsic data characteristics. This approach reveals how different layers shape the final visualization and is evaluated using both quantitative metrics and a human user study. Coming to the proposed method, we align the activations of a frozen model between two streams, a set of real images and a synthetic image under optimization. We support two use cases, visualizing class neurons and intermediate neurons. Starting with class neuron visualization, we began by selecting the target class neuron, in this case, the class agaric, inside a pre-trained architecture. We randomly sample n real images from the target class. These provide the reference feature distribution we want the synthetic image to reflect. We forward these real images through the frozen network and collect activations. In parallel, we initialize a noisy synthetic image and forward it through the same frozen model, extracting activations at the exact same blocks. We specify which blocks to align. Here, they are selected as block 1, 2, and 3 in this example. This enables us to capture the multi-scale statistics of the class. We optimize the synthetic image using sort matching laws at selected blocks with jitter, total variation, and L2 priors for stability. As optimization proceeds, early features guides edges and fine textures, while deeper features enforce semantic structure. We validate class visualizations across architectures, including ResNet50, ConNext Base, and BIT Large, showing that the distribution alignment principle generalizes beyond a single backbone family, unlike other existing methods such as deep immersion. Quantitatively, we compare our method with Fourier, Mako, and deep immersion. We report top-1 accuracy of generated images as a faithfulness check, FID as a realism measure, and clip zero-shot alignment as a perceptual proxy. For intermediate neurons, we pick a specific hidden unit at some layer to probe what that unit actually encodes. We identify top K images from the dataset that strongly activate this neuron. These serve as anchors of what evidence the unit consistently responds to. We forward these real images through the model and collect activations at prior blocks, the blocks that contribute upstream to the target neuron. As before, we initialize a noisy synthetic image and forward it through the frozen model, extracting activations at the same blocks. We choose a small set of blocks, which are block 1 and 2 for this example, at which we'll align distributions with sort matching. This localizes the supervision to the pathway that feeds the neuron. Unlike class neuron visualizations, intermediate neurons requires us to know where to match. We therefore obtain explicit supervision from the neuron via an attribution method. For our case, it is LRP, layer-wise relevance propagation. LRP provides relevance maps for each prior block, indicating both the path that contributes to the target neuron and the strength of that contribution. Practically, we use these relevance maps to weight activations during alignment. We apply sort matching on relevance-weighted activations so that only evidence that truly supports the neuron shapes the synthetic image. We again optimize the synthetic image using sort matching laws at the selected blocks similar to class neuron visualization. To aid inspection, we overlay a transparency map that visualizes the agreement between the neuron visualization and the top K image patches that activate the neuron the most. We provide visualizations of small circuits for two interesting classes of ImageNet. For each class, we find the three most relevant neurons in the penultimate layer of ResNet 50 based on LRP relevance scores, and visualize these neurons through Vital and Mako. In comparison to Mako, Vital achieves higher interpretability. To complement automated metrics, we conducted a human user study focused on interpretability. The study includes 3 tasks. In the first task, participants see a class name and a feature visualization, and we ask them to rate how well the feature visualization matches that class on a 1 to 5 scale. In the second task, participants see top activating crops for a hidden neuron and that neuron's feature visualization, and we ask them to assess correspondence on the same 1 to 5 scale. Finally, participants see only the feature visualization, and we ask them to write a short label or description. We compare these to ground truth by sentence embedding similarity using universal sentence encoder. Across all 3 tasks, the results are consistent. Vital significantly improves class-level faithfulness, neuron evidence alignment, and human labelability of feature visualizations over prior methods, producing clearer, less repetitive, and more semantically coherent images. Like prior feature visualizations, ours are not fully photorealistic and may lack spatial coherence for non-rigid objects. The field also lacks exhaustive benchmarks and well-defined metrics for inner neurons, making standardized comparison difficult. Looking ahead, we plan to extend Vital to medical domains and explore downstream applications on representation learning. This was the end of my talk. Thank you for listening. If you have any questions, feel free to contact me. For further details, please visit our project website from the QR code.